Okay, hello everybody. Welcome to lecture number 14 of MA 180, 190, 186 Calculus. So we're going to continue our discussions from last week, and really this week's two lectures we'll be seeing some really important and pivotal concepts that played a really key role in the development of mathematics throughout the 20th century, and that is the distinction between countable and uncountable sets. So for the moment, I'm not going to exactly recall the content of last week's lectures in any detail, except to mention that we were talking about the notion of countability of infinite countable sets. So what we saw last week was that we have this idea of being able to place an infinite set in bijective correspondence with a set of natural numbers, which are the counting numbers 1, 2, 3, 4, etc. So last week we saw two key things. We saw that the integers can be placed in a bijective correspondence with the natural numbers. And one way of doing that we talked about was to list the integers starting at 0 and then taking alternatingly positive and negative integers as we move away from 0. So the list would have started at 0, 1, minus 1, 2, minus 2, 3, minus 3, and so on. And by continuing that way, we can organize all of the set of integers into a list, which means exactly to put them in correspondence with the natural numbers 1, 2, 3, 4, 5, and so on. And so we say that the set of integers is a countable set or a countably infinite set. And the more surprising thing, I think, in last week's lectures was that we can do the same thing for the set of rational numbers, even though the set of rational numbers geometrically is quite different from the set of integers. Its elements are packed densely into the number line as opposed to spread along it sparsely. But we were able to see that the rational numbers also can be organized into a list. They can be assembled into an order so that we can say in this particular listing of them, there's a first one, a second one, a third one, a fourth one, and they all appear. So that's the notion of countable. An infinite set is countable if it's possible to organize its elements into a list so that in that sense they correspond to the natural numbers 1, 2, 3, 4, 5, and so on. So that's not our immediate theme this morning. I think it's kind of even more interesting. The concept of countable becomes more interesting when you see an example of a set that is not countable. And that would be our main content tomorrow, which is really, in my mind, one of the highlights of this course, to see that the set of real numbers, in fact, fails this criterion of having its elements listable. So it can't be put into bijective correspondence with the natural numbers. So my suggestion for the moment is kind of keep that in the back of your mind. We're not immediately going to return to this idea of countability, but it should be kind of at the back of our minds, but just at the back. We'll be coming back to it very quickly. But in the meantime, today, we're going to introduce another concept that applies to subsets of the real numbers. And I suppose kind of what we're kind of talking about is, we're dealing with these infinite objects. And we have different notions of how you measure kind of the size of something. And if you have a finite set, then a kind of notion of how big it is can be captured by how many elements it has. And that's reasonable most of the time. If we're talking about subsets of the real numbers, I suppose there isn't a kind of concrete notion of how big a set is, or even of, when one set is bigger than another. So you can say certainly that the set of rational numbers is bigger than the set of integers in the sense that every integer is a rational number, but there are loads of rational numbers that are not integers. So the set of rational numbers is a proper superset of the integers. In that sense, it's bigger. But as we saw last time, the rational numbers can be put in bijective correspondence with the integers. So in that sense, you could say they don't have different numbers of elements. They're if you try to, you can list the elements of both of them. So in that sense, they kind of could be regarded as having the same magnitude in terms of their numbers of elements. So another notion that kind of captures a concept of how big a set is this concept of boundedness that we're going to talk about today. And it's a different concept it's a different notion of how big a set can be, which is unrelated to the one really of countable or not. So bounded and unbounded subsets of the real numbers. I think it'll be important for us to have a clear notion in our head of what boundedness means. It's I think intuitively not a very difficult concept, but the language that goes with it can be a little bit formal. So it can take a little bit of practice to just read about it. So essentially, we're talking about subsets of the real numbers. And the real numbers live along a line, as we know. So here's a picture of the number line. And we say that a subset is bounded if on the number line, the elements of the subset are basically confined to the region between some specified pair of points. So a set is bounded, a set of real numbers is bounded if its elements don't extend indefinitely to the left or to the right on the number line, that there's some point beyond which they don't go to the right of it, and there's some point beyond which they don't go to the left of it. So basically, a subset is bounded if it's contained in the interval, open or closed interval between A and B for some real numbers A and B. Okay, so that's the concept of a bounded set. And of course, we can talk about left and right bounds for a set, but a set is bounded if it's confined within some interval. So in that sense, you could say that kind of bounded sets are somehow kind of contained. They don't extend infinitely far to the left or right. So in that sense, they're sort of, they're in some notion, they're smaller than unbounded sets. But this is a completely different notion from the notion of cardinality and of countable and uncountable sets. So here's the more formal version. So if we have a subset of the real numbers, so we've got a subset X of the real numbers for here. If X is a subset of the real numbers, then we say that X is bounded below if there's some real number A, such that all the elements of X are to the right of A. So basically, A is less than X for every element of X. So if the elements of X are denoted by little red dots here, they could occupy sort of contiguous regions of the real line, or they could be scattered points. But let's just say they're denoted by, they're colored red. So X could be some collection of numbers or points on the number line like that. So X is bounded below if there's a real number A, which is less than every element of X. And of course, if there is an A, if there is such a number A, so for example, that one that's labeled there as A, if A is in this case called a lower bound for X, the elements of X are supposed to be indicated by the points that are colored red. So if A is a lower bound for X, then any point to the left of A is also a lower bound for X. Okay, so basically, if a set has a lower bound, it'll have lots of lower bounds. So X is bounded below if there's a real number A for which A is less than every element of X. And whether or not A belongs to the set X, well, A won't belong to the set X if it's less than everything in X, but it could be less than or equal to. So set X is bounded above if there's a real number B to the right of all the elements of X. And the set is called bounded if it's bounded both above and below. Okay, so there's this idea of a set that can be bounded above or bounded below. If it's not bounded both above and below, then it's referred to as being unbounded. Okay, so a set is bounded if it's contained within some interval of finite length in the real number line. That's the notion of bounded. And so, of course, it's, I think a good way to get used to this concept is to just write down examples of sets that are bounded and sets that are not bounded, sets that are bounded above but not below, sets that are bounded below but not above, and so on. So here's a few examples. First example, Q, the set of rational numbers, is unbounded. Okay. Rational numbers can be as big as you want. There's no limit to the extent of the set of rational numbers as you travel to the right on the real number line. So it's not bounded above. No matter how far you travel out to the right, you still encounter more rational numbers. So maybe I should write that down. That's really useful. If it isn't, just ignore it. So the set of rational numbers is unbounded, and Q is it's bounded neither above nor below. And what that means, to say that a set is not bounded above, means no matter how far we travel, in the positive direction or to the right in the number line, we'll never pass all the rational numbers. We'll always encounter more of them. We always encounter more rational numbers or more elements of Q. Okay, and that's, we know that the rational numbers are densely packed all along the number line. There's no stage where you sort of pass the end of them. So, and same for the left, of course. If you travel to the left, the negative direction, you'll always keep encountering rational numbers. You'll never pass the end of the set of rational numbers. The set of natural numbers. So again, in case anyone has forgotten all the different shorthand notations for all these number systems, the set of natural numbers is the set 1, 2, 3, 4 positive integers, counting numbers, whatever you want to call them. That set is bounded. It's not bounded above, because again, no matter how far you travel out to the right on the number line, go to 10 million, 20 million, 50 million, you'll still meet more natural numbers. You never, you know, they increase without bound. But the set of natural numbers is bounded below because the natural numbers are all positive. So as you travel to the left, you will eventually pass the number 1 as you travel in the negative direction. And after that, you won't meet any more natural numbers. So 0 and any negative number, and any number between 0 and 1 indeed, are lower bounds for the natural numbers. So 0 is a lower bound for n, for instance. So is -1 or -2 or -5/4 or anything like that. Yeah, anything to the left of 1, basically. So the set of natural numbers is bounded below because it does have if you travel to the left in the number line, you do reach a stage where you don't meet any more natural numbers. But if you travel to the right, you don't. So it's not bounded above. If you take any interval between a pair of specified points, like the open interval from 0 to 1, that's bounded. There's nothing in it that's to the right of 1. There's nothing in it that's to the left of 0. If you take the closed interval 0, 1, that's bounded. Again, there's nothing in it to the right of 1 or to the left of 0. If you take the closed interval from 2 to 100, that's a bounded set because it's contained between the mark that labels the number 2 and the mark that labels the number 100. So again, I think that's really kind of a good sort of visual concept to have in mind for boundedness, that a set is bounded if there are some specified points on the number line representing the particular numbers, so 2 and 100 or whatever it is, and everything in the set is contained in the region between those 2 points. That's what it means for a set to be bounded. Okay, and remember, bounded, this is another thing that can be a little bit confusing, the precise usage of the terms and definitions. If you say that a set is bounded, you mean it's bounded both above and below. Okay, if it's not bounded both above and below, you say that it's unbounded, but you can be more specific sometimes. So for example, it might be bounded on one side, but not the other. And there are other examples where, you know, you have to kind of know something about the way the set is written in order to figure out whether it's bounded or not. So for instance, if you take the set of the cosine of all real numbers and ask yourself, well, is that set bounded or not? Well, that's kind of a tricky one. You have to kind of think about, well, what kind of values can the cosine of a real number have? And we know that the values of cosine, the cosine of a real number is the x-coordinate of a point on the unit circle. So it's confined between 0 and 1. It can't be anything. So the set of all cosines of real numbers is bounded because the cosine of a real number can only have values between -1 and 1. And maybe that's a useful example to think about as well if you're thinking about bounded sets, because if you think about the graph of the cosine function, so this is a little note relating to example 4 up there. The graph of the cosine function, the domain of the cosine function is the full real number line. So 0, let's say, is here somewhere. The cosine of 0 is 1. The cosine of pi over 2 is 0. The cosine of pi is -1, and so on. And the graph of the cosine function looks like this. This is pi over 2. This is pi, and so on. Same on the other side. So the graph of the cosine function is, you know, if you look at that thing as actually kind of an object in two-dimensional space, in the horizontal direction, it's kind of infinite in extent because the domain of the function is all real numbers. So there are points on that graph with every x-coordinate. But in the vertical direction, it's not infinite in extent. It fits in between the horizontal line through 1 and the horizontal line through -1. So basically, the set of y-coordinates of points belonging to that graph, which is the set of cosines of all real numbers, that's a bounded set. It's actually exactly equal to the closed interval from -1 to 1. But in particular, it's stuck between those two. It's stuck in that band between y equals -1 and y equals 1. It doesn't step outside of that. So the set of y coordinates of points in that graph is bounded, which is exactly what it means to say that the set of cosines of real numbers is bounded. Okay, the fifth example there is an important one, which also relates actually to the current homework and potentially to some questions that appear variously in exams in the history of this course. So if you have a set that's finite, then it must be bounded, because if you have a finite set, then its appearance as a set of points in the number line is just that it's a bunch of a finite set of real numbers. So they might have 5 elements or it might have 500 elements, doesn't really matter. On the number line, it's a finite collection of dots. So there's nothing, there's nothing there except these particular points. In a finite set, it could have 20 elements, it could have 300 elements, it could have 2 elements, but whatever they are, they're a finite collection of dots on the number line. So not only is it bounded, but the elements have to be ordered exactly from left to right. There's a first one and a last one, and certainly it's contained in that interval between its least element and its greatest elements. So all finite subsets of R are bounded. They have to be, because in order for a set of numbers to proceed, indefinitely in the positive or negative direction on the real number line, it has to have an infinite number of elements. If it only has a finite number of elements, they can be ordered from the smallest to the largest, and there'd be nothing to the left of the smallest one and nothing to the right of the largest one. So that's something worth thinking about as well. So, a finite subset must be bounded. There's no way it can fail to be. If it only has a finite number of elements, you can just order them from left to right, and there's nothing to the right of the rightmost one or to the left of the leftmost one. Okay, so that's the concept of bounded, and I guess it's it's sort of a concept about kind of somehow geometrically it sort of captures something about how big a set is, how far it extends around the number line. But it's a different concept of how big a set is from the one involving cardinality. Okay, but we should be able to recognize bounded and unbounded sets. And of course, I'm sure you're no doubt familiar with thinking about the term bounded in relation to functions. So a function is bounded if the set of its values is a bounded set in this sense. So the cosine function, for example, would be referred to as a bounded function because its values can't stray outside the interval from -1 to 1. They're contained in there. Okay, anybody have a comment or question about that? We can take a breather for a second anyway. Okay, if no one has a question, let us continue. So we are still interested in cardinality, and we're interested in this idea about whether you can place infinite sets in correspondence with the natural numbers or not. So in terms of thinking about bounded and unbounded sets, a question that you might ask is, well, bounded sets are, in terms of their extent on the number line, they're contained in specified regions. Okay, unbounded sets are sort of spread out all over the entire line. Their elements stretch infinitely far to the right or to the left, or both. So could it be possible that a bounded set could have the same cardinality as an unbounded set? Okay, in this sort of geometric sense, the bounded set is smaller in the sense of how much space it takes up on the number line. But in terms of how many elements it has, does it have a relation to that at all? It's sort of what we're asking here. Can a bounded set, could its elements be put in bijective correspondence with the elements of an unbounded set? That's what we're asking here with this question. If we go back to the concept of cardinality. Okay, so to think about that, this is kind of really setting the groundwork for tomorrow when we're going to talk about the cardinality of a set of real numbers. But first of all, we're going to talk about some intervals. Okay, so what we're going to do in the next section, the next example, we're going to do this. We're going to show that, yes, in fact, this is, I don't know whether it's kind of good or bad. It seems kind of unsatisfactory to me the first time I see it. It is possible for an unbounded set to have the same cardinality as a bounded set. And in fact, not only that, but the full set of all the real numbers, which is this huge thing. All the points in the number line, all possible decimal representations of numbers, whatever way you look at it, that we claim that set of all real numbers, with magnitude sort of stretching them, as far to infinity, actually has the same cardinality as the set of real numbers that are just contained between 0 and 1, or between 0 and 2, or between -25 and 35, or any finite piece of the number line. So we're going to see in the next example, and this is another thing I think that for many people sort of challenges our intuition, that the set of real numbers actually has the same cardinality as any open interval on the real line. So from 0 to 1, or from 2 to 5, or from 300 to 10,000, or whatever. Okay, so that's a striking thing, that the set of all real numbers whose magnitude distance from 0 stretches as far as you want is actually, in the sense of cardinality, can be put in bijective correspondence with just the set of real numbers in any particular interval between two specified points. Okay, so I claim that this is true, and I claim, in fact, that we have all the tools that we need to be able to see it already since some time back. And so we'll see that in the next example, which is the last one in section 2.3. But before that, one thing to note is that all open intervals, all non-empty open intervals at least, have the same cardinality as each other. Okay, so remember what an open interval is. An open interval, the open interval from A to B. So just to recall, the open interval from A to B for real numbers A and B with A less than B. So when basically A is a point to the left of B on the real number line, is defined to be, the notation for it is just A and B enclosed in round brackets like that with a comma between them, which is another notation that's overly used in mathematics because it can mean different things in different contexts. But it's the set of all numbers x that are between A and B, not including the endpoints themselves. So the word open means that the endpoints themselves are not included in the set. I'll just make a note of that in case. If they were included, it would be the closed interval from A to B. So we're talking about the open interval here. And the assertion is that all non-empty open intervals have the same cardinality as each other. And in other words, that their elements can be put in bijective correspondence with each other. And there's a little exercise here, which I think is probably worth doing, just to persuade yourself of this fact. I won't do it all here, but maybe we'll have a look at one part of it. So the assertion here is to show that the open interval 0, 1 has the same cardinality as, for instance, the open interval from -1 to 1, or the open interval from 1 to 2, or the open interval from 2 to 6, or the open interval from 10,000 to 10 million, or whatever open interval you might like to think about on the real number line, as long as it's not empty, so as long as its left and right endpoints are different from each other. So to see why this is true, well, the open interval from 0 to 1, I'll try to draw a picture. The open interval from 0 to 1 includes, so here's 0, here's 1. And the open interval from 0 to 1 includes all the real numbers that are between 0 and 1, but not 0 itself and not 1 itself. I'll draw it in a different color there. So the kind of open circles there at the endpoints are supposed to indicate that the number 0 is not included in this open interval, which is colored in pink. And the number 1 is not included there, but everything in between them is. So 0.1, 0.2, 0.34, 19, 7, 10, 3, whatever. So anything with a decimal expansion that starts with 0 point string of decimal digits is in this set. Okay, and the claim is that this open interval from 0 to 1 has the same cardinality as, for example, the open interval from -1 to 1. And the appearance of the open interval from -1 to 1, well, it goes from -1 to 1. I'll color it in orange. Otherwise, it looks similar. So it's all the points in between -1 and 1, not including those two endpoints themselves. So, you know, they have the same kind of shape. They're sections of the number line, but the one from -1 to 1 is twice as long as the one from 0 to 1. Yet the assertion is that they're in bijective correspondence. And certainly, you know, one of them is a proper subset of the other one. We've seen before that that's no obstacle to having the same cardinality. So we shouldn't be kind of too mystified by that, or we shouldn't be alarmed by it at least. So the claim is that that an open interval of length 1, this is an open interval of length 1, meaning that the distance from its left-hand endpoint to its right-hand endpoint is 1. And -1 to 1, for instance, is an open interval of length 2. So they're, you know, one is twice as long as the other. So in some sense, it has sort of twice as many elements. But as we know, this kind of notion of how many elements a set has kind of falls apart a bit when you're looking at infinite sets. So certainly, if you take the open interval from 0 to 1, you can relate that to an open interval from 0 to of length 2 by just sort of multiplying everything by 2. So like if you take everything in the set open interval 0 to 1 and multiply it by 2, what you get are exactly all the real numbers that are in the interval from 0 to 2, which is an open interval of length 2, and you get all of them, and you get each of them exactly once, because, you know, multiplying by 2 gives you a different answer for every number that you start with in the open interval from 0 to 1, and it picks up all the numbers in the open interval from 0 to 2, because everything in the open interval from 0 to 2 is twice something in the open interval 0, 1. So basically, by multiplying by 2, we can establish a bijective correspondence between the elements of 0, 1 and the elements of 0, 2, the open interval. That doesn't answer the first question here, but it does take us from an open interval of length 1 to an open interval of length 2. So for the first one, we could say that taking the function that takes x to 2x, this gives us a bijective correspondence between the open interval 0, 1 and the set of doubles of all the elements of that, which is the open interval 0, 2. Okay, if you're in doubt about that, which would be quite reasonable, try it out for a few numbers. You know, basically what I'm saying here is that you can get anything, any number between 0 and 2, any real number between 0 and 2, by multiplying something in the open interval 0, 1 by 2. So everything in the open interval from 0 to 2 arises that way. And if we apply that kind of operation of multiplying by 2 to different things in the open interval 0 to 1, we get different answers. You know, if you're multiplying by 2 is a one-to-one function, it doesn't take two different things to the same thing. So so this idea of just doubling takes us from the open interval 0 to 1 to the open interval 0, 2, and we can reverse it by just dividing everything by 2. That'll take us from 0, 2 to 0, 1. So this doubling idea gives us a bijection between an open interval of length 1 and an open interval of length 2, which already tells us, well, yeah, okay, intervals of different lengths can have the same cardinality. What we're actually asked for here is not a correspondence between 0 and 1, between 0, 1 and 0, 2, but between 0, 1 and minus 1, 1. And the reason I've harped on about 0, 2 is because it has the same length as the open interval from minus 1 to 1. So after we've done this, after we've multiplied by 2, we're now kind of in the open interval from 0 to 2, but we can just slide back to the interval from minus 1 to 1 by just subtracting 1 from everything. So then subtract 1 from everything. So just subtract 1 from everything to get from 0, 2 to minus 1, 1. So in other words, if we take the function that takes x to 2x and then subtracts 1, so think about what that does and apply that function to elements of the open interval 0, 1, which is this pink line here. The multiplying by 2 part takes us from the open interval 0, 1 to the open interval 0, 2. And then subtracting 1 from everything there just slides us back so that we land in the open interval minus 1 to 1. So this function, x going to 2x minus 1, is a bijective correspondence between 0, 1 and minus 1, 1. Okay, so that's kind of the idea, or an idea, that we can use to establish that all open intervals have the same cardinality as each other. Basically, this is, I think, usually how people approach it. Start with the open interval 0, 1. If you want to put that in bijective correspondence with the open interval from 10 to 100, first thing to observe, when you're going from an interval of length 1 to an interval of length 90, so multiply everything by 90, that brings you from the interval 0, 1 to the interval from 0 to 90, and then just slide it up and down the number line to get the interval that you actually want by adding or subtracting the appropriate number. So basically, if you wanted a bijective correspondence from the interval 0, 1 to the interval from 10 to 100, multiply everything by 90 first. That brings you to the interval 0, 90, and then add 10 to everything. So it will be like x going to 90x plus 10. That would establish that correspondence for you. And no matter what open interval you have in mind, you can do that. Just like do a scaling, multiply by something, and then do a translation up and down to bring you to the interval that you want. So what this tells us is that all bounded open intervals have the same cardinality as each other. By this idea of scaling plus translation, we can establish a bijective correspondence between any open interval of finite length and any other one. So that's that's news maybe, or maybe it's not news, maybe you already knew that, but in any case, it's something that's notable about open intervals. They all have the same cardinality as each other in terms of this concept of cardinality for infinite sets, which let's just recall, two infinite sets have the same cardinality if it's possible to put their elements in bijective correspondence with each other. So for two infinite sets that happen to be open intervals on the real number line, this is a way of doing it. We can, we can scale and translate. And I guess actually one thing I didn't say is if you wanted to establish that the open interval from 1 to 2 had the same cardinality as the open interval from 2 to 6, if you want to, you can sort of go via the interval from 0 to 1, which is kind of the default one, and do the scaling there and then do the translating. So that's something that will work as well. Of course, in this particular case, if you wanted to go from 1, 2 to 2, 6, you have an interval of length 1, and you want to bring it to one of length 4. Yeah, probably the easiest way to do it is to go back to, is to first of all slide back to 0, 1, then multiply by 4, and then translate to where you want to go. So in any case, I mean, yeah, this concept of a scaling, a dilation or contraction, which is the multiplying by the appropriate number, combined with a translation, will allow you to establish these correspondences between all open intervals of the real line. So I mean, I suppose the mechanics of doing it for particular examples is not so crucial. The key thing is to sort of see the idea that that's a mechanism for doing it. Okay, so that kind of answers the question, at least, of whether it tells us the different bounded sets that occupy sort of different regions of the real number line certainly can have the same cardinality of each other. We haven't answered the question about whether a bounded set can have the same cardinality as an unbounded set, because this mechanism that we've just talked about in this item, exercise 43, in the slides, that deals with bounded open intervals. So to deal with unbounded ones, we are going to look at another example. So this kind of function, x going to ax plus b, is not going to take us from a bounded interval to an unbounded one. So we need a different idea if we're going to be able to tackle that one. So the last item in this section, we're going to look at this particular interval of the real number line, and it looks a bit odd, but don't be put off by that. So we're talking about, the reason why we're talking about picking this one will become clear in a minute. We're talking about the open interval from minus pi over 2 to pi over 2. And, pi is an irrational number and sort of a difficult thing to get your hands on and all that, but never mind. It's a number which is roughly around minus pi over 2 is roughly around, it's half of minus 3.14, so it's something like minus 1.55 or so. Pi over 2, that is, not pi over 6, sorry. Don't know why I said that. Pi over 2, and plus pi over 2 is over here. Again, it's something like 1.55 roughly. So pi over 2 is over here. And the open interval between minus pi over 2 and plus pi over 2, looks like any open interval on the real number line. It's sort of symmetric around 0, and it's got all the numbers in that range. So, it's the very same as the open interval from minus 1 to 1 in terms of its geometry and general appearance. Okay, why are we picking that? We'll see in a second. Okay, the claim is that we can show that the full set of real numbers has the same cardinality as this open interval from minus pi over 2 to pi over 2. And hence, because of the content of the last example, the same cardinality as any other open interval in the real number line. This particular one is convenient for showing this, but we've already seen that by scaling and translating, we can put this interval in bijective correspondence with any other open interval on the number line. So, the fact that we've picked this one for the example doesn't sort of matter so much. You could have picked 0, 1 or 0, 2 or whatever, and just put it in bijective correspondence with this particular interval first. Okay, so if we were going to believe that, and in order to do it, we would have to establish a bijective correspondence between that open interval and the full set of real numbers. So we'd have to have a scheme that would match every real number. And remember, the real numbers, like that's every single point on the number line extending without bound in both directions. We'd have to say that we'd have to have a mechanism for matching to every real number. So 20 billion or 0.00001 or minus 304, whatever, with some particular number in the range minus pi over 2 to pi over 2 in such a way that every real number gets matched to a different number in here and that everything on both sides gets used exactly once. So every real number would have to have exactly one sort of partner in this interval from minus pi over 2 to pi over 2, which seems like a tall order. You know, we've got this really huge, very unbounded thing and this little interval. And we have to be able to sort of stand over this correspondence that we're going to describe and say, yeah, we're sure that every real number gets matched to a different thing in here. So fortunately, a mechanism for doing this is ready-made for us. It comes to us from calculus and trigonometry, and that is nothing but the tan function. So let's think about, so the claim is that the tan function is bijective on this interval, that it maps everything in the range minus pi over 2 to pi over 2 to a different number, and that the range of tans of all numbers in that interval covers the entire real number line. And not only that, but it does it in quite a nice way, that it just increases throughout that interval from minus pi over 2 to pi over 2. So let's see if we believe it. Okay, that's the idea. We're going to argue that the tan function is a bijective correspondence between the full set of real numbers and this little interval from minus pi over 2 to pi over 2. Okay, so let's recall what the tan function actually does. This picture is not very legible probably, so I'll make an even more illegible one. Okay, in fact, I'll insert a new page here. Okay, so we're talking about numbers between minus pi over 2 and pi over 2. So if we draw just the positive, or the right-hand side of the unit circle, so it passes through the point 1, 0, and we're talking about kind of the open version of that. So 0, 1 and 0, minus 1 are not actually part of our picture, but they're the very edges of it. So everything in between is in the picture. We draw it in green. So we've got the part of the unit circle. So the green line, this is the part of the unit circle whose points have positive x coordinates. So we're basically leaving out the parts whose x coordinate is 0. Okay, and the circumference, the length of that green curve is pi, because it's half of the circumference of the unit circle. So basically, if you take a number in the range minus pi over 2 to pi over 2, so let's say you take x, some number between minus pi over 2 and pi over 2, then you can visualize it as a distance, either if it's positive, you can take the arc length of length x as we travel in the positive direction from 1, 0. So if x is positive, take the arc length x as you travel upwards from 1, 0 in the counterclockwise direction around the circumference of the unit circle. And the point that you reach after traveling a distance of x along the circumference is the point whose coordinates are cosine x and sine x. Okay, that's how cosine x and sine x are defined. And if you take the line segment that connects that to the origin, tan x is cosine x over sine x. Sorry, tan x is sine x over cosine x, which, sine of x is the vertical height of that point above the x-axis. Cosine of x is its horizontal separation from the y-axis. And so sine x over cosine x is just the slope of this line segment. So the slope of this line segment is the tan of x. So x, to start with, was a number in the range minus pi over 2 to pi over 2. Okay, it's either positive or negative. If it's positive, take the arc length of length x as we travel in the positive direction counterclockwise up from the point 1, 0. stop when you've traveled the distance of x. The point where you are has coordinates cosine x and sine x. And so if you just think back to the definition of slope and look at the line segment that connects that to the origin, its slope is the vertical height over the horizontal distance. So it's sine x over cosine x. That's the tan of x. And if you look at the slope of those line segments, when you start at when x is 0, you're looking at a horizontal line segment, the slope is 0. So the tan of 0 is 0. As you travel in the positive direction away from 0, the slope of that line increases from 0 continuously through all the positive real numbers, and it approaches infinity as you get up here towards pi over 2. So this, the slope of this line segment, think of it as if we were in person, we could draw kind of animation. We could think of it as kind of rotating from, like the hand of a clock, from 1, 0 up around to pi over 2, except that it's traveling anti-clockwise. As you do that, its slope increases from 0 through all the positive real numbers. It's approaching infinity as our x approaches pi over 2. And as we go in the negative direction, if x is negative, we take an arc whose length is the absolute value of x in the clockwise direction from 1, 0. And here, the slope goes through all negative values from 0 all the way down, approaching minus infinity down here. So basically, think of it like the hand of the clock as it rotates through the whole right-hand side of the right-hand half plane there. The slope of that line segment goes all through all the real numbers from minus infinity to plus infinity. There are no different angles for which it has the same slope. So it goes through all the real numbers, captures each of them exactly once, and establishes a bijective correspondence between that interval minus pi over 2 to pi over 2 and the full set of real numbers. So again, if you're thinking about this, like it is quite an intricate thing to think about. So, we have a bijective correspondence between the interval minus pi over 2 to pi over 2 and all the real numbers. So just to kind of bear in mind, where exactly are the numbers here between minus pi over 2 and pi over 2 in this picture, and where are the real numbers? The elements of this set from minus pi over 2 to pi over 2, they're the sort of distances from 1, 0 as you travel. So here, down here, the distance from 1, 0 along the circumference of the unit circle is approaching minus pi over 2, or x is approaching minus pi over 2, we're down on the negative side. As we travel through values minus pi over 2 towards 0, to all the negative values in this interval, the slope of this line segment, which connects us to the origin, is traveling from minus infinity up to 0. Then as we travel to the upper quadrant there, where our element of the bounded interval is traveling upwards from 0 through the positive numbers as far as pi over 2, and the slope of that orange line segment is increasing from 0 to infinity as that happens. So the real numbers in the correspondence, this is supposed to be a bijective correspondence with the real numbers. The real numbers are the slopes of the orange line segments that are increasing from minus infinity to plus infinity as our hand of our clock moves from pointing downwards vertically to pointing upwards vertically, rotating through. And the numbers from minus pi over 2 to pi over 2 are basically like the arc lengths from where we are on the unit circle to the point 1, 0. So that's how the correspondence works. And so the tan function just sort of does it for us. It gives us this bijective correspondence. And it's established for us. Yeah, the set of real numbers is in bijective correspondence with the interval from minus pi over 2 to pi over 2. And because we know that all open intervals in the real number line have the same cardinality as each other, that tells us that they also all have the same cardinality as the entire set of real numbers, which is another, kind of surprising thing when we think about cardinality. That, and I suppose what it tells us is that cardinality is not any kind of proxy for the notion of kind of the length that a set occupies along the real number line. It just isn't like an infinite interval. The entire real number line can have the same cardinality as just the bounded region between 0 and 1, or minus pi over 2 and pi over 2, or whatever. So that's another kind of concept that we have to embed into our working knowledge on this topic. What we are going to talk about tomorrow is, which we haven't talked about yet, is the question about whether this cardinality, which is the cardinality of the real numbers, the interval 0, 1, the interval minus pi over 2 to pi over 2, and any other open interval, whether that cardinality is the same as the cardinality of the natural numbers and the rational numbers or not. So we haven't talked yet about whether these things are countable. That's tomorrow's content, and it's another, I think, very well, it was something that was very surprising to the mathematical establishment when that question was first posed and first answered by Cantor around the year 1900. So we'll talk about that tomorrow. And the second remark there is that this interval sort of seems like an odd choice, but the reason we make it is that the hand function is sort of ready-made to answer the question first there. So just a remark, we're certainly done for today. This section 2.3, I think, contains some very sort of challenging ideas. So just want to sort of acknowledge that in case anyone else thinks so. And ideas that I think most people take a bit of time to make friends with. So it's one of those things where you kind of have to reflect on it and come back and go away and have it sort of bubbling away in your subconscious. And it starts to make more and more sense as you keep sort of thinking about it patiently. I think that's kind of my comment on that. Of course, everyone experiences these things differently, but I think that will be the experience of a lot of people. So a couple of things just to recall, what have we actually talked about? The concept of bijective correspondence for infinite sets, the concept of two infinite sets having the same cardinality, and in particular, the natural numbers having the same cardinality as both the rational numbers and the integers. And then the last highlight, I suppose, was the fact that the full set of real numbers has the same cardinality as any open subinterval. And I suppose that the example of the tan function sort of explicitly giving that correspondence between the real numbers and the interval minus pi over 2 to pi over 2 is an important one, which is worth having somewhere near the forefront of your mind. Okay, tomorrow we're going to talk about whether that set is countable or not. So I'm going to stop the recording there, and thank you very much to everyone.